Hello. Oh, yes, it works. Okay. Hi. I'm really happy to be here at DjangoCon. It's really exciting. It's my first DjangoCon. I was in DjangoCon Europe a couple years ago. So I'm going to today talk about Postgres index types, and even if my title contains something referring to a very bad movie, I'm mostly going to be talking about crocodiles and not Harry Potter references. So just about me, I'm a software engineer at Citus Data that got acquired by Microsoft a few months ago, so I'm now a Microsoft software engineer. Before that, I've been a Python developer for years, and I also really love databases, as weird as that sounds. I kind of tend to be more specialized in Postgres. I did co-found Postgres Women about a year ago. We realized that there were not that many women, and we kind of wanted to prove that we exist. And now we're trying to work a little bit more on, different diversities, because white women are not really diversity. If you want to follow me on Twitter, I'm Louise Meta, and I have a blog. And I'm mentioning this blog because mostly I did write a very long series of articles that take the content of this talk. I wrote the first version of this talk about a year and a half ago, and what I did to prepare for this talk was read the entire source code for, indexes in Postgres, and that was a very painful thing. And it was because there was no good content on that specific thing. So I ended up writing what I needed. So today we're going to talk about indexes. So first, I'm going to give you kind of a reminder for those who are new to databases and Postgres and Django and everything. So what are they for? And then we'll go through kind of the options that you have when you create indexes. And then we'll go through 4 different types of indexes and how they are internally implemented in Postgres. And I kind of, on purpose, decided to not talk about 2 types, which are spgist and hash, because I've never met someone who actually needs that. So, So, I was talking about crocodiles. So here is the example that I'm going to use for this talk. You have crocodiles. It's a table that contains, email, first name, last name, number of teeth, very important, and the last checkup. And they can take appointment because they need dentist appointment. And the birds are, the doctors. This is like a really realistic example because in nature, the crocodiles, get their teeth cleaned by birds eating the food. So it's really, everything I say is true. So what are indexes for? The first thing I'm going to talk about is constraints. I know that it's not necessarily the first thing you think about when you think indexes, but constraints are very important. So when you create a primary key or a unique constraint or an exclude constraint, it will be transformed in the database into an index. So that you can see, like, if you connect to your PSQL and you look at your table, you will see indexes appearing that are a note as primary key or unique constraints here. Here I have a weird exclude that prevents a crocodile to take 2 appointments at the same time. We also use them for optimizing queries. That's basically often the main reason we create index. So why are they helping? The idea is that in an index, you're going to have the value of the row, of the column that you're indexing, and a pointer. And instead of reading the entire table, it's going to go to the index and search for the value that you're looking for. If that's not clear, kind of think about it as an encyclopedia. If you want to read about crocodiles, you're not going to read the entire encyclopedia from A to Z. You're just going to go to the index, look for crocodiles, and go back to the pages. So, creating indexes. To create an index, here I have this query. I want the crocodiles that have 10 teeth, and I want to optimize that query. It takes about 30 milliseconds to execute. So what I do in Django, it's really easy. In my model, I just add in the field dbIndex equal true. And it's going to create the index in the database. You can also use raw SQL. I do that a lot, so no judgment here. You can do create index and then give an index name. This is optional on the table and the column that you're doing. And so here it really helps. I mean, 6 milliseconds instead of 31, it's pretty good. You can also create unique indexes. For that, again, in the field, here I have emails, and I want my emails to be unique, which kind of makes sense. So you can just have a unique equal true here. In raw SQL, it transforms into create unique index. Again, you could give a name here. So what will happen is when you try to insert a row with, twice the value louise@croco.com, that's not my real email address, it will fail with key already exists. And now fun stuff, because that was kind of, basic. So you can also create partial indexes, which is really cool. Here in my database, I have appointments, and 95% of them have been already done. Like a bird took care of it. So I end up with that field done equal true for most of my rows. And let's say most of my queries are going to be on done equal false, and I want the emergency level bigger than 8. So basically, I would just want what appointments are not done and an emergency. I could create a simple index like this, just on emergency level. But what I can also do is create an index with a condition. Here, it's available from Django 2.2, so if you don't use it, you'll have to do some raw SQL things. So here I add the condition done equal false in my indexes. And so it's going to generate the following thing. Thing is not the right term, but so create index with a where clause. So why is it great? It's great so first the size of my index here is much smaller. I had 13 megabytes, and now it's like 350 kilobytes. So really it's smaller. And also now the time of my query is actually 10 times faster than with a normal index. So that really is a good trick, especially like if you have some soft deletes. Let's say you have a forum, the people can delete their messages, but you don't, remove them from a database, you mark them as deleted. This can be the kind of use case where a partial index is pretty good. You can, of course, do partial unique indexes. Again, like my email, let's say I have history, and I can't actually have a unique constraint on the entire table. So I can say, for example, oh, okay, now I had a unique constraints on email with a condition that it's been created after 2019, September 1st. That is also available Django 2.2. And it transforms into create unique index again with just the where clause here. Again, it will create an index that will be much, much smaller. So here it's not just saving disk space. That's a very good thing in general. It's also that we're going to have much faster inserts. Because when you insert and there's a unique constraint, Postgres will go through the index and check that you're not breaking the constraint. So having a smaller index will actually help you a lot in terms of performance. And again, if you have soft deletes, like your users, they can delete their account, but they can rejoin, but with a new account. That's a good thing to do, to have like a unique index on email where deleted equal false or something. But with GDPR, you should just delete the data. Just saying. So you also have multi-column indexes. So here I have appointment. I'm filtering the appointment for a specific bird, and we want to know kind of like just the appointment that the bird did that are an emergency. And I kind of want to optimize that. So here I create an index, and in fields there are 2 columns. So in raw SQL you do a create index on table, and instead of having just 1 field, you have 2, 3, 4, 5. Just don't go too crazy about that, but you have more than 1 field. There are 2 things that you have to know about multi-column indexes. The first thing is that you can actually reuse your index. The reason is so I decided to do this little thing with colors because I wanted to be able to explain that in simple terms. So if you have your index, and so it's indexing the values, and here basically I have the first column is the plover bird ID, and the second one is the emergency level. In the index, we'll order by plover ID for the first column, and then for each plover bird, it will be ordered by emergency level. So what you can see is that here, the first column is ordered. The second is ordered by plover bird by emergency level. So here it's the goes 6, 10, 10, and then 1, 6, etc. So it's actually not ordered overall. Only the first column is. So you can reuse that index if you're doing just a simple filter plover bird equals value. So that would reuse the index. It's important to note that because you might, if you need a multi-column index, then you might also want to clean the useless indexes that could be just reused by this one. So that's the first thing. The second thing that you have to think about is that you should put your most filtering column first. That means that at least try. It's not always possible. This is like very theoretical. Here I have 75,000 appointments that are emergency level bigger or equal than 9. And I have 5 appointments that are from this bird. Here, when I do the index with plover bird and then appointment, it will look only, it will get the 5, and out of the 5, filter on appointment level, emergency level, sorry. If you did the opposite, it would actually be filtering out of 75,000. So you can actually, I've had that problem a lot at Citus where people are like, oh, I created that multi-column index and it actually doesn't really help. I'm like, let's try to see actually what order you used, because that does change a lot. And so now a little bit of fun with Postgres and index types. The first index I'm going to be talking about is btrees. It's the default index, so everything that you've seen before, just btrees. Nothing crazy about that. So when you do create index, it's just going to create a btree. So what is a btree? It's a balanced tree. That's the first thing. The difference between a balanced tree and a binary tree is that first all the leaves are at equal distance from the root. This is the root, these are the leaves. And a parent node can have multiple children, it's not only 2. So that means that the depth of the tree will be smaller, which is good when you're going to search into the tree to kind of limit the amount of, changing the reading head between pages. So right now I'm talking about pages, and because I don't want to scare anyone, I'm just gonna say a page is basically where everything is stored, almost in Postgres. It's an 8 kilobyte data structure. It's nothing crazy. It's just that the name is page. So in an index, what is a page and what does it contain? It contains a block number that is going to be used for the pointer. It's going to define a high key. And what is a high key? It's the high, basically in that page, any item will have a value lower or equal to the high key. And then it has items, and we'll go through items later. So I was talking about high key. So here, for example, maybe in the back you don't see as well. I'm sorry. I hope you do, but not sure. Here I have this page has the high key 16. So it means that I will only find crocodiles with 16 or less teeth. In this one, the high key is 31. So it will be 31 or less. And here I don't have a high key because it's the last page of the level. So you kind of don't know how many teeth a crocodile will have. It could be like 100, yay, or less probably. And now there are also items. And the items basically contains the value and a pointer. That was what I was describing before. The value will be basically just the value of what you're indexing, of the column. And the pointer will be in the leaves, the pointer to the row. In the parents, a pointer to the children. So to sum up, you have a btree is a balanced tree. The values that are indexed are the values of the rows. And I know this sounds very trivial and very obvious, but it's not the case for every index. That's why I'm saying it. The data is stored in pages, and the pages have a high key and items that are pointing either to a child page or to the row. And so why are btrees so good then? They're very good for anything where you compare data. Like, is it equal, bigger, lower, bigger or equal and lower than or equal? Why? It's basically, again, like you are indexing the value in a structure with high key. The high key really matters when it comes to the binary search. And that's what Postgres is using to search into the tree. It's going to do a binary search. So btrees are good for almost everything that you want to do. Like, really commonly, you won't need anything else than a btree. But when you do, there are other types. And the second one I will talk about is Gin. So Gin is used to index arrays and JSONB TS vector. TS vector, for those of you who are not necessarily, don't really use that, it's full text search in Postgres. It will basically just transform a text into a series of vectors of lexem, which is basically just the root of the word. It's efficient for these operators, which probably don't mean much. This is basically anything that would be like, oh, does this array contains this value? Does this array contains this array? Does this element, overlap to that? For full text search, for example, it's really good because you're going to be wanted really often to have like, oh, is that word in that text or something? So here I added a new column. It's the heel teeth, and it's what the crocodiles got hurt and the ploverbird dentist had to repair. So here I randomly generated this. This is not my real, I think that this would be a lot of teeth damaged, but yeah. So I created a Gin index, and so how do I do that? Postgres is very good with Django, and Django is amazing. And so you have in Django contrib Postgres indexes, Gin index, and basically Django supports all the different types of indexes that Postgres provides out of the box, so it's really easy for you to use that. So you can just simply create a Gin index with the fields. If you're using raw SQL, because you love SQL and it's fun, I guess. I mean, I do. Yeah. You can create index using Gin. That's how it works. So how is it different from a btree? Earlier I was telling you, in the btree, we just index the value as it is. If we were to use a btree on an array, it would just index the entire array. What Gin does is that it's going to take the array and split it. And each value will be an entry in the tree. Each value is unique. So here what you can see is, this is again my array of heel teeth. And it was actually split. And so this branch of the tree will contain all the crocodiles that have the teeth 1 healed. And this one will have the 4, 6, and whatever. And the difference is that, so in a btree, each element of your table has an item in the leaves. Here, instead, what there's in the leaf is a list of all the crocodiles that have the teeth 1 healed. When, sometimes the list just becomes so big that it just doesn't even fit in the page anymore. And what happens in that moment is that what we do is we have a posting tree which just contains also pointers to crocodiles or rows that are just stored in a tree instead of in the page. So here I have the time that I showed that example because I actually created an index, a btree index, just to show that it would actually not even be used by PostgreSQL when executing the query. So here it used to take 160 milliseconds, even with a btree index. And now it takes 41 milliseconds. And you can see here in the bitmap, there's a bitmap index scan and on my index. For those of you who don't really know what that comes from, it's an explain plan that you can actually execute on your query within PostgreSQL, just to kind of see whatever is done when executing a query. So to sum it up, so Djinn is also a balanced tree, so that's pretty close to a B tree. And each value in the tree is unique. Instead of just indexing the row, we split the value, and each value is an entry, a unique entry in the tree. So it's very efficient for full text search and overlapping data, etc. And I'm going to speak about gist. So gist is an index that is a little bit weird because it is a framework. So you could write your own gist index for your own data if you have time and patience. So it provides, like if you look into it, and there are articles on my blog about this, but if you look into it, there's like a list of functions that you could implement for any data type that you would have, and that would do a gist index, sorry. So what is the difference between a gist index and a btree or a Djinn? The first thing is that the data is not ordered in it, which seems weird, but does make sense. Weirdly. Here, I created a weird data type for an integer range, just to show you that here, you can see that here it's 3 to 5, the range, and then here it's 0 to 2, and here it's 48, so it overlaps and it's not even ordered. Why is it this way? If you're using gist index, it's most likely because you're using, PostGIS, and using geometry and everything. What happens is in a geometry, if you think about it a little bit, it makes sense that it's almost impossible to build a tree on a geometry that just never overlaps. Geometry, like if you take two big circles, it's pretty, like you will have some overlapping. So when you build a gist index, there will be overlapping, and that's something that has to be taken in account. So the same value can be inserted in several places, which is why if you build your own gist index, you'll have to be very careful because you can end up with bad performance, but you can trust the people who build gists for PostGIS. When you create a gist index, again, it's very simple. It's in contrib Postgres indexes. You can just use gist index, or again, you can use create index using gist. So it's why use a gist index for any overlapping things that you would want to do with, whether it's geometry, array ranges. The main test I did with gist for this talk was on a TS range, and that's a pretty good example, I think. It's, well, again, especially used for PostGIS and for nearest neighbor operations. It's also used very commonly for full text search. And there are some very, if you want to use full text search and you want to use Djinn or gist, there are several differences between them. I don't think I have time to talk about them right now, so I'm going to pass that. If you have questions about it, I'm happy to answer them in the hallway. I'll be probably hanging out at the booth, not Postgres, sorry, Microsoft. Where do I work? Booth, sorry. Damn it, it's filmed. And the last one I will be speaking about, Brin indexes are amazing. I love that. So they are very different because they're not even a tree. It's the only index that is not a tree. So it's something that we call block range index. And what it contains, and be careful because it's going to be very confusing until I show you what it is that it's going to have a group of pages that are physically adjacent, and the range of value that this adjacent block range contains. So it makes Brin indexes very, very small and good when you have to fast scan like really, really big tables. So what I mean with all of that is that here I have a Brin index on created at. So for the pages from 0 to 128, I have the range 2008 to 2009, July something. Then 128 to 256, it's 2009 to 2010 something. So here you can see how a Brin index is. But be careful, because it's not always good. In this case, like if I just try looking for 2013, I know it will be here, but if you want to use it for a birthday column, that will be terrible, because all the ranges will be really big. So when you use a Brin index, you have to be careful about having values that have a correlation with the physical location of your data. So basically, any data that actually increments would be a good thing. You also have to be careful about deletes, because when you delete data from, I don't know, 2 years ago, whatever, and then you vacuum, the space is then reused, and then your ranges are really bad again. So it's something to think about when you want to add a Brin index is correlation and not deletes, which again, GDPR, ugh. So when you create a Brin index, again, super easy, Postgres indexes, Brin index, you add it to your meta and indexes, and that's it. So conclusion, a btree is great for any comparison operators. Gin are good when it comes to arrays and when it comes to full text search, when you have to kind of have, this array contains whatever. Gist are good for overlapping, especially for geometry. That can also be used for full text search, and Brin are really good when it comes to fast scanning large amount of data. Thank you for your attention. Yeah, that's it.
All right, so we have time for one, maybe two questions at the.
I was curious about GIN use on, you said JSON-B. It would be used on JSON-B. Specifically, I was curious about like depth, how that's handled. Can you only index on like an array or keys or?
From what I remember, it's on the keys. But you know what? I'm not sure. Because I would guess the keys. I've only mostly used GIN indexes for full text search, actually. So if you're curious about that, there are like some pretty good extensions to Postgres where you can actually, that's what I was showing for Brin, you can actually go and analyze what the pages contain. So when it's things like that where you don't know exactly what is indexed, you can use these extensions to go and see that.
Hi, can you elaborate a little bit on how you handled regulatory things like GDPR or CCPA? Like, did you hard delete the rows or did you scrub them? And if you did scrub them, like, how did you handle certain constraint issues?
Okay, so is the question on constraints or on Brin and handling a Brin index? I'm not sure.
Specifically with like how you address GDPR or CCPA.
Okay, so in my company that I worked for before, what we had was a very complex, I think that anyone has a complex system, where, so our constraints had conditions for deleted accounts, and then after 6 months, I think, of an account marked as deleted, we would delete all the data, because legally we have to, I think.
Okay, that's it. Thank you.